Wow, that was a long last minute. I think I sat here for a couple hours waiting for that last minute to go by. Well, hey, welcome everybody. Welcome once again to Astronomy Daily Live. So hope everybody's doing well out there in the universe and the world. Yeah, things are good here. Took it a little bit easy today in terms of work. I was up a little bit late last night, and just so yeah, today was just one of those days to sort of take it easy for a while. Just not do very much of anything whatsoever. Just sort of played with the data that I collected last night, and I'll get into that a little bit here. But let's see. I want to go over to the chat and see what's going on over there. I don't see anything. And Nightbot isn't responding again. So don't know what's going on there. If there isn't too much of a chat, maybe somebody let me know. Either you can post something over on my Discord server. There's a link to down below. All right. Well, so it looks like things are going. Hey, okay, good. I'm seeing some actual beings on the other side of these things. You know, you guys do a pretty good job passing the Turing test. I think, okay, there we go. So Nightbot just sort of woke up and blasted every response out that I did there. So cool, excellent. So yeah, things are good here. As I said, just sort of took it nice and easy today. Played with a little bit of the data. That's about it. But yeah, the Turing test, for those of you who don't know, is a relatively simple test, right? You sit yourself down at a terminal, right? So you have a keyboard and a screen, right? And you can type messages into that screen, right? And have a conversation with, well, and that is sort of the Turing test, right? If you right can have what you would determine to be a reasonable conversation, right? Then that thing, whatever it is, person, AI, will have passed the Turing test, which means that you are dealing with, as far as you're concerned, an intelligent entity of some sort. But who knows, right? Anyway, before I blather on too long, I want to make sure to say howdy to Bobby on the panel. Hey.
Hey, what's up, everybody? Welcome.
So how's everything over there today, Bobby?
Everything is fine and dandy.
Fine and dandy. I like it. And I'm looking at the chat, and I'm seeing that Tom is in there. Hey, Tom. Chuck is in there again. Cheers. Tim Robinson is popping his head in. Hey, Tim. Nice to see you. Cheers. Yeah, cheers. Okay, well, so last night's obsession was a success. My apologies for the technical difficulties. I actually rewatched the entire video today to see where I cut out and how much you actually lost. And I got to say that it actually cut out at the perfect moment, because what I decided to do was move to.
I'm going to disconnect and reconnect right quick. I'll be right back.
Okay, very good. So so yeah, I decided to go for R Leonis first. Now this is a Myra type variable star, which means it varies in brightness quite a bit, and also has a pretty long period. I forget exactly what R Leonis is, but I think it's something like 300 or so days. And Bobby is back.
Yeah, yeah, see, I'm using my Bluetooth headphones now, and they sometimes have a little lag.
Oh, a little bit of a lag. Okay. Yeah. Technology. So yeah, so I opted to go to R Leonis right away, and so yeah, I don't think very much was actually lost. Nothing relevant, really. I think I'm trying to remember. I was yeah, no, I did all the messing around with trying to point, to different stars. I got that on the live stream. I'm just trying to remember what part you all actually missed, and yeah, I don't know, but it came back. I pushed the right combination of buttons apparently, and it all came back just fine. And so I was ready to proceed to go to R Leonis and see if I can collect some data on that. Don't need a lot, right? I just need a little sample, right? Just a little bit of a photon grab. They don't mind. So yeah. Hey there, Tim, on the panel. Howdy do.
How is everybody?
Everything's good. Everything's good.
Hey, what's up, Tim?
Hey, Bobby, how are you diddling?
All right, and you're making me want to fart.
Oh, I felt bad this morning.
Yeah, I inadvertently heard about that. So that's all I can say about that. Just wow. Yeah.
Never again. Never again.
Well, Alan Parsons, he came out with an album that's called Try Anything Once. So there you go.
Yeah, but I did 3 spoons and then a bloody big spoon afterwards, so more fool me.
Well, as I just said, you got to try everything once. If that's what you think you should go for, far out.
Lesson learned.
Anyway, so I had nothing but trouble with all 3 of my targets last night, trying to find them.
Did you not know that yesterday in his live stream, he actually, Tim Robinson, did a ghost pepper challenge.
Yes.
Excuse.
I did hear about that. That's why he gets the salute. He gets the cosmic salute. All right. Anyway, so yeah, I had absolutely nothing but trouble. Right. I think the pointing was probably actually pretty good, but for some reason it was all on me. There, I was not seeing those patterns, and you know, I can't put the blame anywhere else except right on me, just not seeing them, and just staring and staring and staring and staring and trying to find the patterns, and then all of a sudden just bang, it pops in, and then I know where I am on the sky, and I can move the telescope to the target, grab data. So, I mean, in each case, I did do that, but I did take much more time than what I wanted in terms of actually finding these things. Putting these targets into the CCD field of view, right? So that's just that's a challenge, and it's a thing that I'm just going to have to practice at, and hopefully get better as time goes on. Sometimes it seems I can just bang it out, no problem at all, and sometimes it's like yesterday, where it was just like, man, I cannot see anything. And then when I do see something, I like completely misinterpret it, right? So that just ends up setting me off on a weird tangent that actually right at the end of the video, right? I said that I had to come inside here and look up the coordinates again, because I'm looking at my screen, right, and I'm seeing some star patterns, right? It's not as if I'm not seeing them, but trying to match them up to the chart just wasn't working. But it was all right there. It was all there each and every time.
We want to welcome Andy Calloway in the chat.
Hey there, Andy. Nice to see you in the chat. So yeah, it despite having a little bit of trouble getting these targets into the field of view, I was completely successful. I got 100 images of R. Leonis, and 100 images of a nearby star that I will use as a comparison star or a reference star. Because I actually looked it up, and R. Leonis is just a couple weeks, maybe 30 days or so past its brightest point. And I actually let me pull up my Discord, and you can see that plot, which I've posted over there for everyone's enjoyment. Let me share my screen. Share it like that. Go like that. Come up here. Go over here. So this is the latest. Oh, that's really big. So this is the latest magnitude data. And these, excuse
Bless
me.
you.
Thank you. These open.
Tight.
Yes, sir. I think that was about a 7.5 or so.
7.9.
Okay. Well, I appreciate that. But yeah, I don't know. I mean, it definitely wasn't an 8. So I really didn't. I'm trying to be a little bit civil here. So, and this is not the Olympics. So, all right. So yeah, these open circles are visual observations. So these are people who are going outside and using a telescope, right? And putting an eyepiece on their telescope and looking. And they are making a guess based on, the surrounding stars, and, the same way that I'm going to do it, right? I sort of use a reference star. So it's exactly the same thing, except I'm going to make a measurement, and I mean, they're making a measurement, but it's a different kind of measurement. So as you can see, it looks like it peaked, right? Maybe about 5:30 here, and now it's about almost 5:70. So it's been about 30 to 40 days since it's brightest. And this is actually one of the things that threw me when I was trying to find this target, was that it is really, really bright right now, right? It's getting close to 7th now, right? I mean, 6.5, 7. So it's still really, really bright. And so a 2-second exposure, which is what I was doing, produces a very, very large signal. And I'm saying there are no bright stars there, right? And then I look around and it's like, wow, that's exactly where that star's supposed to be. And it's like, yeah, it must be that one. So yeah, it's that kind of stuff that just, it's going to throw me a little bit. But anyway, so yeah, this was a nice way to confirm that it actually is quite bright, right? It'll get down to maybe about 10th magnitude or so at its dimmest. So that's quite a magnitude swing, right? That's what it looks like. It peaked at about 5.5, and if it goes down to 10, then that's 4.5 magnitudes, and every magnitude is a factor of 2.5. So 2.5 to the 4.5 says, so this peak here is about 62 times brighter than this down here. So yeah, I mean, it's a significant amount. So yeah, it's kind of nice, to catch it when it's bright, I guess. I mean, I would have been happy catching it anywhere. It doesn't really matter. So this will be sort of an ongoing thing because, it's such a long period. As I said, something like 300 and some days, I think, from peak to peak, something like that. And so, yeah, the idea is just sample this whenever I'm out. Take 100 images just to have sort of a decent signal to noise. The more images, the better. So, 100 is a nice round number. It doesn't take a long time to get those images. It takes maybe, I don't know, 20 minutes, maybe, something like that, maybe a little bit less. then yeah, you know, make the measurement and see how it compares to what these kinds of plots are showing, and you know, if I think that it's you know, good enough to contribute, then I will. So, all right, well, that's that. Let's see. I was just I showed off a few raw images here. So here's Pallas, the asteroid Pallas. There's some background stars. As you can see, you know, this is the raw data. So you're seeing all kinds of bad columns here and pixels that are hot, right, all the time. So it's kind of a messy thing, but that's okay. That's, you know, it is what it is. Yep, is what it is. So you know, that's to me, this looks absolutely fantastic. Looks really good. So there's that. Here's our Leo. So you can see that it's like super bright. It's this big blob. So I'm just scaling this such, or stretching it such that I'm looking at very low levels here. So there's a natural spread in these point sources, and due to the optics, it's primarily an optical effect. It's extremely low level, so it doesn't really, you know, contribute much. But because I have this thing stretched, because I like to see the noise, right? I don't like to hide all the noise, right? I like to see it. So this shows, you know, sort of the top of the noise, and then all this stuff, all these stars, they sit on top of that. So, but yeah, this is very bright. About what? I think that plot said maybe about 6 magnitude or so. So that's really bright. And then Eros. So there's faint little Eros. And yeah, again, you know, noisy data hasn't been reduced yet, hasn't been dark subtracted or flat fielded or calibrated in any way. Just raw data right off the camera.
How come those columns are always vertical? Don't you get any horizontal ones?
It's how this camera this array of pixels is wired. That's all it is.
Right.
I think yeah, I'm pretty sure that it's probably read out from, in this case, from bottom to top. So it's probably got like what's called a shift register in it. So, you know, this first row moves up, and then, you know, out of the camera to the computer, and then the next row goes, and the next row, and the next row, and the next row. So yeah, this is just a readout.
Right, that
thing.
kind of makes sense.
Yep. Yeah, it just you know, I've got a nasty pixel right there that's just sort of bleeding into everything. So, but you know, that's how it goes. All CCD cameras are like this. There are different grades, so you can get better ones than this that are you know, either completely clean or you know, maybe 1 or 2 defects. But this guy has a few, but it's not a big deal. It all comes out in the wash, so I have absolutely no problem with it at all. But you can see, you know, the stars here. Jing, jing. This guy. This is a little binary. Here, do you see that other
Now, I
one
have
right there?
a question about Cosmic.
Yep.
Yeah, so I have a question about CCD cameras and stuff like that. Can you actually make your CCD camera work with your Fedora machine, or is better XP?
I don't believe that there is anything for Linux. I think the only camera control software that is available for this camera runs on Windows machines. And there are lots of, well, not lots, but there's at least a couple or a few pieces of software that could run my camera. But yeah, I've just, I've just sort of, like I've explained to you before, I've got a system that works as well as, well, it works extremely well. So there's no way that I can improve it without pretty much completely changing everything, right, including the camera. So with the situation that I have, and the hardware I have, I've actually got the best situation possible. And hey, I'm happy with that, right? I have no problem with that. But if there's an opportunity to upgrade, I certainly will. So you never know. Anyway, so there's Eros there, and yeah, I was just I noticed that this is a little binary there. Now, whether it's a true binary or it just so happens the line of sight, they look really, really close. Who knows? But these guys are pretty close. Every pixel on here, and you can actually see the pixels, right? Every single pixel on this image is almost 2 arc seconds in size. So if we come down here and make a rough estimate, right? So here's sort of the center of this one. So 1, 2, 3, 4, 5, maybe six pixels down, and 1, maybe 2 pixels over. So 6 pixels down and 2 pixels over. We're going to do a little bit of math here. We're going to do the Pythagorean theorem. So the distance between here and here squared equals the sum of the square of this distance and the square of that distance. Let's see, it's probably like a squared equals b squared plus c squared. So yeah, so let's do that. So 6 squared is 36, and 2 squared is 4. So 36 plus 4, and then we're going to take the square root of that. So that's about 6.3 pixels from here to here, right? From sort of the center of this blob to the center of that blob, or the brightest points. 6.3 pixels. Every pixel, as I said, it's a little bit less, but it's approximately 2 arc seconds. So let's multiply by 2, and we'll know the distance. So 12.6 arc seconds between that guy and that guy. So that's pretty close. But it happened all over the place. So
thank goodness your calculator is still working.
Well, it's causing some consternation, because that one digit is not coming back.
That.
Yeah. So I still need to give it a bang, and maybe I will Anyway, so then,
So,
oh, go ahead.
So probably a good time to get a calculator by now, huh?
Well, who knows? Who knows? I don't know what direction I'm going to go. I'm going to be a lost soul, I think, without this one. So, you know, I'm gonna have to mourn for, you know, at least a few days. You know, wear some black and stuff. Anyway, so here's just a couple other little things I did. I took the first image of Eros and the last image of Eros, and I stacked them. I had to rotate them and translate them a little bit to get, you know, the background stars to stack. But as you can see, Eros here is moving a substantial amount. I think that's about an hour's worth of motion there. So it went from way over here to way over here. And there's our binary again. So
talk about warp speed.
Yeah, so it's trucking along there. So again, you know, this is the raw data, so it's a little bit messier, you know, than what it sort of appears. But I'm just looking at the data values here, right? So you know. Anyway, so there's that one. So that's Eros, and then I did the same thing for Pallas, and you can see that Pallas doesn't move as much, and I think that's a combination of probably, you know, it's just not moving as fast as Eros, but I think there was a lot less time on this one. I did 200 images, I think. So that would have taken, let's see, about 5 times 200 is about 10,000 seconds. So that's 10,000 seconds? No, 1,000. 200 times 5 is 1,000. Sorry, 1,000 seconds. Gee whiz! I was like, wow, that's a lot longer than what I thought. Yeah, so that takes about 17 minutes or so. So this is only about 17 minutes of motion, where the Eros one was an hour of motion. So I think, yeah, you know, now that I'm thinking about it a little bit, it sort of seems as though, you know, maybe they were moving pretty close to the same rate. Don't know. As you can see, my star alignment on this isn't perfect. You see how this guy is sort of wiggling back and forth. So I didn't get things exactly aligned, but this star is supposed to be stationary, just like that one and these two. But this guy is definitely moving for sure. So that's pretty fun. Fun stuff. We've got clouds here tonight. So that's, I think that's pretty much why I'm not out. It's because of those clouds. It was nice and clear all day. Oh yeah, I made some movies of my data acquisition. So I know that you're not going to be able to see this really well. So I've got 100 images of R Leonis and then 100 images of the reference star that I've just made into a movie. Right, so this one here with these two stars next door to it, that's R Leonis itself. And then that other single star that you see right there, that is the reference star that I'm going to use. And as you can see, the tracking isn't you know, it's not the best in the world. I have to constantly, well, almost constantly correct it. That's okay. That gives it the, you know, the special touch, right? This is not a automated system. This has got my personal touch, is on all of this data. So there's that one. I've got a similar one for I've got a similar one for Palace.
How you was able to take those images and put them in a video?
Haha. It's well, you know, it's kind of funny because you what popped into my head was it's magic, right? Well, it actually is. There is a it is basically a Unix tool that has been around for a long time. It's called Image Magic, and it's a set of commands that allows you to do all kinds of things to images. And one of the things that I can do is use this program called Convert, which will convert a FITS image, right, in the scientific data image, and convert that to like a JPEG image, right, or a GIF image, or a PNG, whatever it is, right? In this case, I converted these to JPEGs. Then I used another image magic program called FFmpeg, which allows a series of images to be input, and an AVI, or like an MP4 video, to be produced. So that's how I do it. I just convert, you know, the FITS images to JPEGs, and then stack them all and put them in a video like this. So here's Palace, and so that's a little bit more jittery, and I actually have an explanation for that. I changed the slew rate of the telescope, just because I wanted to see, you know, if that sort of made it more likely or better to you know, keep these things in the screen as opposed to, you know, to drifting out. And yeah, I really don't like how much it's jittering around. I mean, it's okay. My software will be able to deal with that, but yeah, don't like it. So anyway, this bright guy here is Palace. What's that, Bobby?
I can hear dogs.
Oh yeah, yeah, it's a doggy alarm. Anyway, so there's, yeah. So there's Palace, and I've got somewhere down here, I've got Eros.
I gotta say, Linux rocks. All I gotta say is Linux rocks. Windows suck.
Well, you know, I've come to the conclusion that it's sort of like, you know, to each his own. You know, if you like Windows, okay. But yeah, I got introduced to Unix as soon as I got at the university, and absolutely loved it for its, you know, relative simplicity, but underlying incredible power. So I like it. Anyway, here's Eros, this guy right there. It's kind of hard to follow, but as you can see in this sequence, you definitely actually even see motion. of the asteroid. Now, what I'll do in software is I will make all these images such that the stars aren't moving at all. And so the only thing that you'll see...
Chuck says you got a nice shot of Pallas. I'd like to welcome Patrick Meddy in the chat.
Hey there, Patrick. Thanks, Chuck. Yeah, well, you know, I'm not going to know if this data is any good until I look at it, make some measurements and all that. And that's sort of the next task. You know, today was just sort of a fun day to, you know, make a few of these and see how that goes. So that's really fun. Nice and fun. The one thing that I think I'm going to start doing, I'm going to stop sharing, is I think I'm going to start actually recording my target acquisition sequences as well, because you know, I mean, for no other reason, it'll be a good laugh, because you know, I'll know in hindsight, right, where the target is, and I'll be able, you know, to look at the screen and be like, it's right there. It's extremely obvious, right? While I'm doing it, it is not obvious at all. It's a hard task. So I think it's sort of like, you know, I want to treat this like you know, when like sports teams practice, you know, they video record their practices and their games and all that, and then afterwards they watch it, right? Because you learn a lot that way. And so I want to do exactly the same thing. I'm going to record my target acquisition sequence, and you know, I mean, it could be a long one, it could be a short one, I don't know, right? But then I can later on make these movies I was just showing you, and I can watch how I did it, and you know, see if I just wasn't seeing it, or if I was just so completely off, you know, that I wouldn't. No idea. All right. Well, cheers. Cheers to photons.
Yeah, I've got faucet water here. Cheers.
Excellent. Yes, I've got the HOH here, that well-balanced molecule. All right. Well, great. Let's. I'm going to look at the chat really quick and see what is going on. The monkeys and I are just fine. Good. Good. Nice to hear that. Ah, you crazy kids. Crazy kids. Don't know what we're going to do with you. All right. Well, you know, we haven't done in a little while what I haven't done in a little while, and I'm looking at the time and I'm like, yeah, I think this is going to work out really well. I want to go over to the bleeding edge of astronomical research and see what's going on over at the research notes of the American Astronomical Society. So let's dive over there. RNAAS, pronounced RNAS. And let's see, I'm going to get, okay, we can start here. So I've got my screen ready, because, you know, I like to keep up with these kinds of things, and that's what this live stream is about, is us, you know, sort of going on this journey together, just, you know, following my nose and see where things go. Usually relatively interesting. also usually way over my head, like that. So but that's okay. That's all right. You know, we need to reach. We need to stretch. And so that's a good way of doing it. You know, stretch your mind, as they say. So I am going to share, and you know, I think I must be like a mind stretching addict or something because I really like that. Just like, yeah, I don't know. I wonder if that's
I've got to stretch my mind just to walk and whistle at the same time.
Well, you know, a good stretch is probably a good thing anyway. So very, very healthy. So any kind of stretch is usually a pretty nice one. All right, so I'm going to share my screen. I hide that, and let's go over to the research notes of the American Astronomical Society. Hopefully these things are still free. I'm waiting for that to drop. I don't know if it ever will. But okay, so here's the latest ones, and as you can see, they're into volume 3, which makes sense. It's March. Oh, sorry, volume 3, number 3 is in March. Yeah, that makes sense. It's their third year. Okay, let's see what we've got here. So a new binary star system in the constellation of Phoenix. Okay. I don't know. I wonder why that's. Is there anything significant about this, or is it just basically saying we found this new binary system of this type? Was discovered it was detected during a search for the all-sky automated survey for supernovae assassin database for previously unreported eclipsing binary stars in the upper right area of the constellation Phoenix.
So what's the title of this again?
A new Ursae Majoris type binary star system in the constellation Phoenix. So there's a type of binary star system that's called Ursa Majoris, right? Which is, of course, in the constellation of Ursa Major, the Big Dipper. And I guess W is sort of the reference for this kind of binary star system. And they just found a system like that down in the constellation of Phoenix. I guess, yeah. So it looks like they just sort of chanced upon it and found it, and there it is. Well, kind of interesting. So it's a definitely some kind of eclipsing binary star. But it's kind of an interesting light curve, huh? Kind of interesting. So this goes through 2 phases. All right, so here's phase 1, and here's phase 2. And the reason why you've got these humps in the middle here is because of the geometry of the orbit. It's actually one orbit. You actually see
Phoenix is a southern hemisphere constellation, right?
Correct. Yeah, they actually give the right ascension and declination here. So negative 4321. So that's pretty low down there. Pretty low. So these deep dips here, right? This one and this one and this one. Those are caused by when the secondary star passes in front of the primary star. These dips, this one and this one, you can sort of see aren't quite as deep, right? Not quite as deep. These are caused by when the primary star passes in front of the secondary star, right? Or the secondary star goes behind the primary star. Its light is dimmed. So you have this double dip thing going on, and I guess it's this kind of a star, right? Binary star system, because of the characteristics of the light curve. There's something about this shape that is like W Ursa Majoris. So that's all it's saying. It's I like seeing actual magnitudes here, right? So this is the V magnitude, the Johnson V magnitude. And let's see, it looks like it's going from about 14.6 up to maybe 14.2. And then here it's, yeah, maybe 14.5, 14.55. So that's pretty cool. This is, yeah, 14th magnitude, 14 and a half. It's a little bit out of my range. I could see this, but it's not going to be very pretty. So okay, yeah, they're just they were rummaging through some old data and found this light curve. So there you go, pretty cool. Near spec L. Yeah. Well, I mean, discoveries are exciting, right? Discovery of 2 faint white dwarf candidates in open cluster NGC 2516. Cool. So they're finding white dwarfs in open clusters. White dwarfs are very, very faint, right? Very, very faint, because supposedly, at least, because they're so small, right? So their luminosity is very, very low, and so for the most part, the white dwarfs that we're aware of are relatively close to us, right? Because they're just really, really faint. But it's kind of neat that they're seeing white dwarfs in open clusters, which are, most open clusters are pretty far away, hundreds of light years away. So that's pretty nice. Let's see. Mass determination is often problematic, right? So they don't really know how many white dwarfs there actually are, right? We don't know. Okay, yeah. So they're using Gaia. We searched a wide field of radius 5 degrees around the center of NGC 2516. Identified cluster members with their proper motions, which is something that we've done here live, and we will probably do again. We could actually do it on the sky if you wanted to. We can think about doing that. Maybe not today, but we could look at the same data these folks were looking at. Let's see, within 2.5 milliarc seconds per year, and parallaxes within 0.75 milliarc seconds. Okay. So 6 stars. Not quite sure if I'm okay. 6. I got you right. 6 stars that look like they're part of the cluster and has photometric characteristics of white dwarf stars. White dwarf stars don't look in terms of colors, doesn't look anything like a typical star, right? These things are well, there are lots of different kinds of white dwarf stars, but for the most part, they have very almost featureless spectra, with the exception of, you can often see hydrogen and some helium. You can see other things too, and this is where it gets into the different kinds of white dwarfs. But for the most part, what you see is a pretty clean spectrum. So not a lot of activity there. So relatively easy to identify with Gaia data release 2, because they look at the sky not only with their broadband green filter, but they also have 2 narrower band filters, which they call red and blue. And if you look at the difference between the red magnitude and the blue magnitude for a white dwarf, what you'll notice is that so if you took blue minus red, right, what you would see is that the blue magnitude is much higher than the red. So you would get a positive B minus R value, right? Now, am I doing that right? Is that going to be positive? No, it's going to be negative. Blue is brighter, so blue is a smaller number. Okay, so let's go through that again, because I always mess that up. So if blue is brighter than red, then blue's numerical value is smaller than red. So B minus V is going to be negative, right? So if you look through Gaia and look for negative values on your blue minus red magnitude, chances are that you might be looking at a white dwarf. So yeah, so within a 5-degree radius, they found 6. So that's actually, I'm a little bit surprised. Okay, yeah, and actually here, they actually have that plot. Let's see if we can. Okay. So here, I know it's kind of hard to see, but this is the blue minus the red, just like what I was just like what I was saying just moments ago. And then this is plotted versus the G magnitude, right? So this is what's called a color magnitude diagram. And as you can see, these 6 stars have a negative blue minus red, which means that blue is brighter than red, right? So these are very, very blue stars, very white stars, right? So cool. Okay. Reset image size. Yeah. So let's see. Okay. So I guess, did they narrow it down to maybe just 2? the two stars that were not previously known white dwarfs have positions in the sky that put them fairly far from the cluster center, which is the likely reasons why they were not identified previously. Okay, I gotcha. So four of the identified white dwarfs here were already known to be white dwarfs. Is that am I reading that right? Let's see. Yeah, right. So 4 of them were previously known white dwarf stars. 2 of them, they've sort of come to the conclusion that those 2 are white dwarfs also, based on their colors. So that's all right. So candidate 1 appears to be the coolest of the white dwarfs and possibly the lowest in mass as well. So is this... Yeah. Okay. I think these are just... I guess this is candidate 1, candidate 2. Gaia ID, their positions, their G magnitudes, their colors. Not quite sure what NUV... NUV and FUV. Not quite sure what that is. Dang. All right. Well, that's kind of nice. They determined these from just from Gaia. That's pretty nice. Let's zoom in here and look at these other things. So here's the positions. Kind of hard to see. I wonder, is there a... I thought there was a way to... Yeah, high resolution image. Can we do this? It's gonna completely... Well, that's not much better. Anyway, sort of shows the positions of where the white dwarfs are relative to the cluster. This looks like a very, very rich open cluster, right? So here's position in the sky, right? Well, this is not position anymore. This is motion in the sky, both in right ascension, right, and declination. And as you can see, there's a clustering there because all these stars are more or less moving together. So there's the parallax, which is an indication of distance. And as you can see, can we move this over? Okay, yeah, they're not showing the whole thing, but they're showing where the white dwarfs are in this distribution. And as you can see, you know, even with these relatively large error bars, which is, I guess, what these things are, you know, this could be over here, and this could be over here, and this actually is here. These guys are outside, so their distances are questionable, I guess. Kind of hard to tell. So pretty cool. Pretty nice. So again, you know, this is a discovery, right? That's you know, I think that we're going to get a lot of those in these research notes. A lot of discoveries, because this is the place to, you know, make that kind of announcement, right? Because it's short and sweet. It doesn't have to go really, you know, through any kind of peer review. It just sort of has to go through an editorial review. So yeah, it just takes a couple days. Let's see when this Let's see, where am I going here? Article information, that's what I want. So it was received on March 8th and published on March 15th. So it took a week. That's not too bad. I think they're trying to get it down to like 3 days. But okay, so these guys are out at SDSU. Cool. SDSU is a pretty cool, nice university, right in San Diego. All right, let's finish this out. I think there's only a couple here. Software roadmap for solar system science with the LSST, and predicting additional planets in TRAPPIST-1. So TRAPPIST-1 already has like seven planets. Is it 6 or 7? So, you know, I just think that I just think that's enough. So I don't think they have to look anymore. That's cool. Yeah, they, you know, if you like to get into statistics and all that kind of stuff, this is your kind of paper. Yeah, because I can guarantee you that's what this is all about. Is it's like, well, you know, if it's like this and like this and like this, then we should be able to see A, B, C, and D, right? So, cool. Well, all right, everybody. I think I'm going to get out of here for now. I'm going to look at the chat one more time, as you can see. I'm going to stop sharing.
Excuse
me. Baseball starts in 4 days. Okay. 4 days. All right. All right. Well, I think we're good. Excellent. Well, thanks everybody for coming in once again. Just taking a little bit of time to talk and share astronomical things and space things and sciencey things and all kinds of nerdy things. So cheers to all of that.
I'm empty.
It's a crisis.
I'll have to put the kettle back on.
You're going to have to. All right. I'm going to sneeze one more time, I think. I might. All right. That was a little bit better.
I'll give you a 7.95.
6.
All right. A 6? Dude.
Tight ass.
All right. Oh, man. All right, you guys. I'm going to get out of here for now. So thanks for coming in. It's always great fun. And like I said, I just love sharing the passion. And we've got a great crowd here. So I'm having a blast. And let's do this again soon. You know, I'm thinking I'm going to get over here again tomorrow about 2 hours UTC. Yeah, I think that's a pretty good time. And we'll go from there. All right, buddy. I'm going to sneeze again, so I'm going to get out of here. All right. I'll see you later. Peace,
Okay,
cheers, and all
care,
that.
mate.
Live long and prosper.
Live
Bye-bye for
long and
now.
prosper.
All right, bye.